Hey everyone, I hope you're doing well. In this video, I'm going to be going over some practice problems involving applications of algebraic expressions. Pause to check out the timestamps and feel free to jump around the video by using them in the description. First, I'll go over some practice problems involving rewriting sums and differences using the distributive property and the GCF, or the greatest common factor. Then we'll practice identifying and proving equivalent algebraic expressions. And at the end, I'll go over some geometry applications where we represent the area and perimeter using algebraic expressions. I encourage you to pause the video whenever you need to, whether it's to actually try solving the problem or just to think a little bit. You can replay any parts that you need to hear or see again, but other than that, grab some paper and something to write with, and let's do some math together. In example 1, we're going to practice rewriting a sum or difference using the distributive property and the GCF. Let's start with a numerical expression like 12 plus 16. Right away, we can write that we have one set of this 12 plus 16. However, we can also write this as having two sets of 6 plus 8. And it just so happens we can write this another way, saying we have four groups of 3 plus 4. We can write these three different equivalent expressions because 1, 2, and 4 are all common factors of 12 and 16. While these are all equivalent expressions to 12 plus 16, this bottom one is typically going to be the most useful one to us in algebra. This 4 is the GCF of 12 and 16, and this 3 and 4 are relatively prime. Distributing this 4 to the 3, that's going to equal 12, and distributing this 4 to this 4 is going to equal 16. Let's try another one here, but let's do 27 minus 18. Of course, we can start off by saying that we have one of these 27 minus 18s. 2 is not a common factor, so we can't pull out a 2, but we can pull out a 3 because that's a factor of both numbers. 3 times 9 is 27, and 3 times 6 is 18. While 1 and 3 are common factors of 27 and 18, 9 is also a common factor. 9 goes into 27 3 times, and goes into 18 2 times. 9 times the quantity of 3 minus 2 is equivalent to our original expression of 27 minus 18. Now it's not completely necessary to write out all the different options, even though it's good to understand. Let's talk about how to get the GCF on the outside on the first try. So if we have 27 minus 18, we can use this method called the ladder method. First, you just find a common factor of 27 and 18, and I'm going to choose 9. 9 goes into 27 3 times, and it goes into 18 2 times. This 9 here is the GCF, and this 3 minus 2 represent our relatively prime terms. Let's try a few more together. Let's start with this 30 plus 45. I'll start with a 5 here on the outside because 5 times 6 is 30, and 5 times 9 is 45. Since 9 and 6 still aren't relatively prime and have a common factor of 3, we're going to put that on the outside. 3 times 2 is 6, and 3 times 3 is equal to 9. Since 2 and 3 are relatively prime, we're all done here. Multiplying 5 and 3 together, we have our GCF of 15. And we have this 2 plus 3 down here, which is going to be inside the parentheses as 2 plus 3. This will be our equivalent expression. While you could also write these as equivalent expressions, these don't have the GCF on the outside. Once you find the expression with the GCF on the outside, you can just take factors of it, like the factors of 15 being 1, 3, and 5, and write equivalent expressions. Let's try 21 plus 28 now. Think about your times tables and what common factors we may have. If you were thinking of 7, good job. 7 goes into 21 3 times, and it goes into 28 4 times. 7's our GCF, so we can write it here, and 3 and 4 are left over. Bringing that 3 plus 4 over here, this is our equivalent expression. Let's try 72 minus 60 now. The minus sign doesn't change anything, and the numbers are a little bit bigger here. If you're not sure about factors here, you can at least start with a 2 since they're both even numbers. Half of 72 is 36, and half of 60 is 30. Now that these numbers are a little smaller, we can maybe use a bigger factor like 6. 6 goes into 36 6 times, and 6 goes into 30 5 times. The product of 6 and 2 get our GCF of 12, and the 6 minus 5 here are just going to be rewritten as 6 minus 5 right over here. This is our equivalent expression. Now let's try this 48 minus 32. Well, I know some of you could start with larger numbers. I'm just going to start with a 2 for anyone that might need to. 2 goes into 48 24 times, and 2 goes into 32 16 times. Now for common factors of 24 and 16, I'm going to go with a 4 here. Again, you could use a bigger number, but I'm going to go with 4 personally. And for 6 and 4, they're still even numbers, so I can use a 2 one more time. 2 goes into 6 3 times, and it goes into 4 2 times. No matter what numbers you chose, you should get a GCF of 16, and leftover numbers of 3 minus 2. Bring that 3 minus 2 right over here. This will be our equivalent expression. If you want to check any of these, feel free to do so by distributing. I promise you in each of these instances, we're going to get the original expression that we started with. Now let's try some with variables. Let's start by looking at this 4x plus 12. Between these two terms, the 4 has an even coefficient and the 12 is an even constant. That means that we could pull out a 2 as a common factor. Writing a 2 here on the side, 2 goes into 4x 2x times, and 2 goes into 12 6 times. Seeing that our coefficient of 2 and our constant of 6 are both even again, that means we can pull out a 2 one more time. 2 goes into 2x x times, and 2 goes into 6 3 times. Since we pulled out two 2's here on the side, we really could have just pulled out a 4 one time. And this x plus 3 here are relatively prime, so we can write that down here. This is our equivalent algebraic expression using the distributive property and the GCF. Let's try 15x minus 18. Think about your factors of 15 and 18, and hopefully you come up with a factor of 3. 3 goes into 15x 5x times, and 3 goes into 18 6 times. Since 5 and 6 are relatively prime, 3 must be our GCF. We can group that 5x minus 6 in parentheses and write that right over here. Here's our equivalent expression. If you'd like to, feel free to distribute any of these GCFs to the terms on the inside and see if you end up with the original expression. Now let's try this 14y plus 42. Between our coefficient of 14 and our constant of 42, you should think of the number 7. 7 goes into 14y 2y times, and 7 goes into 42 6 times. Since our coefficient and our constant aren't relatively prime yet and they're both even numbers, we know we can divide them both by 2. 2 goes into 2y, y times, and 2 goes into 6, 3 times. 7 times 2 will get our GCF of 14, and this y plus 3 are our relatively prime terms, and we can write them right next to it in parentheses. This is our equivalent expression, and we can check it saying 14 times y is 14y, and 14 times 3 is 42. And let's try one more. We have 32m minus 10. Since they're both even numbers, we can start with a 2. Half of 32 is going to be 16, so we have 16m, and half of 10 is going to be 5, so we have minus 5. 2 is our GCF, and 16m minus 5 are left over. We can write 2 times the quantity of 16m minus 5. That'll be our equivalent expression using the GCF and the distributive property, and we can check this by saying 2 times 16m will be 32m, and 2 of these negative 5's will get us negative 10. In example 2, let's practice identifying and writing equivalent algebraic expressions. For this first one, the question is whether these two expressions of x plus x plus x plus x and 4x are equivalent or not. To do this easily, you can just pick a number that's either 2 or larger and plug it in for x to check. In general, stay away from making your variable equal 0 because anything plus 0 just stays the same. And stay away from using the value of 1 because anything times 1 stays the same. Whenever you're plugging in hypothetical values, stick to 2 or above. So let's hypothetically say that x is equal to 2. Substituting in on the left here, we'll have 2 plus 2 plus 2 plus 2, and that's just going to equal 8. Substituting it over here, this is 4x, or 4 times 2, and that's also equal to 8. When x was equal to 2, both of these expressions were equal to 8, which means that they're the same. What if you chose a different value, like x is equal to 7? Substituting in, we would have 7 plus 7 plus 7 plus 7, and that'll equal 28. Substituting 7 into 4x, that's going to be 4 times 7, and that's also equal 28. In both of these scenarios, we got true statements. You can plug in any value for x, and both of these expressions will be equal to each other. Since this can be tedious of plugging in the value for x 4 times here, it's important to understand that we can combine like terms so that we can just simplify this left expression to make 4x. If we can say that 4x is equal to 4x, we don't need to do all of this extra work. However, if you want to ever prove that the expressions are the same, choose a value for x, make it 2 or higher, and see that they're the same. And if they happen to not be equal to each other, that means the expressions are not equivalent. Now let's see if these two expressions are equivalent or not. Well, we can make up a value for x right away to check. It's a little bit more efficient if we actually just simplify the left expression since it looks a little bit more complicated. This 4x minus 2x can be combined to make 2x, and this positive 7 and positive 8 can be combined to make 15. Now that we've combined like terms and we can't simplify anymore, let's compare this to this x plus 15. While these 15s match here, these variable terms don't match. These two expressions are not equal to each other. If you'd like to prove this, you can make x equal a value, and I'm going to choose 3 in this case. Again, we're going to choose a value that's 2 or higher. Substituting in, we have 2 times 3 plus 15. 2 times 3 is going to be 6, we have 6 plus 15, and 6 plus 15 equals 21. On the right here, substituting in 3 for x, we have 3 plus 15, and that's going to equal 18. Since 21 is not equal to 18, we know that these two expressions are not equivalent. It's good we didn't hypothetically let x equal 0, because if we did that, we would have said that the left side equals 15 and the right side equals 15 if we plugged in 0 for x. It's important to know that just because something works one time doesn't mean it works every time. Now let's see if these two expressions are equivalent or not. First, notice this 5x plus 3 seems to show up quite a bit here. If you can make quick observations like this, you can tell right away that these two expressions are equivalent already. If you take 4 of these 5x plus 3s and take away 2 of these 5x plus 3s, you're going to get 2 of these 5x plus 3s. Let's prove it anyway. First, we'll distribute this 4 to this 5x and this 4 to this 3. 4 of these 5x's is really 20x, and 4 3's gets us 12. Taking away 2 of these 5x's, that's really going to be taking away 10 of these x's. And taking away 2 of these 3's, we're really going to say that we're taking away 6. 20x minus 10x is going to equal 10x, and 12 take away 6 is equal to positive 6. For our expression on the right, we have 2 of these 5x's, which is really just 10x, and then we have 2 of these 3's, and that's going to equal 6. Like what I said from the beginning, these expressions are equivalent. While we could plug in values for x to prove that these are equivalent to each other, since 10x plus 6 is equivalent to 10x plus 6, we don't really need to right now. Now let's check to see if these two expressions are equivalent or not. The expression on the left can't be simplified, so let's look at the one to the right. Following the order of operations, we're going to have to do multiplication first and complete the distributive property. 3 of these 2x's, or 3 times 2x, gets us 6x, and 3 of these 4's, or 3 times 4, is equal to 12. Remember that every variable has a coefficient. This x, while we don't see a number in front, technically has a 1 that's invisible in front of it. We don't write it because of the identity property, but it's there. So we can write minus 1x minus 5. This 6x and minus 1x can be combined to make a total of 5x, and this 12 and negative 5 are going to combine to make a positive 7. This is our final simplified expression to the right, and we'll compare that to the expression on the left. Hopefully at this point you can tell that these two expressions are not equivalent. 5x plus 8 can't possibly be equal to 5x plus 7. However, if you want to hypothetically prove it, you can let x equal a value. Remember to choose a value that's 2 or higher. I'm going to choose something easy like 10. Substituting in, we have 5 times 10 plus 8, and 5 times 10 is 50, so that's 50 plus 8, and that's equal to 58. Substituting to the expression to the right, we have 5 times 10 plus 7, 5 times 10 is 50, so we have 50 plus 7, and that's equal to 57. Since 58 does not equal 57, we know that these two expressions are not equivalent. Let's just try one more, but this time we have fractions involved. To add these like terms together, we're going to have to get common denominators to add their coefficients. When adding 2/3 and 1/2, we need to find the LCD, which in this case is going to be 6. We can multiply 2/3 by 2 over 2 to get a denominator of 6, and multiply 1/2 by 3 over 3 to get a denominator of 6 as well. Our new fractions will be 4/6 plus 3/6, and combined, that will be a total of 7/6. Combining 2/3 x and 1/2 x, we're going to get 7/6 x. Now that we got the fractions out of the way, at least our constant terms are just whole numbers. 3 plus 4 just get us 7. On the right, we're going to have to start off by distributing this 7 to this 1/6x and to this 2. 7 times 1/6 is just going to be 7/6, so we're going to have 7/6x. And 7 of these 2's, or 7 times 2, is equal to 14. And we can just copy this minus 7 here. This 7/6x didn't have any like terms, so we're just going to bring that down on its own. And this positive 14 minus 7 can be combined to make a positive 7. Here we can see that these two expressions are indeed equivalent. To choose a value to prove it, we can say let x equal something like 6. I know 6 will be a nice number because it will cross cancel with the 6 in the denominators. Here we have 7 over 6 times 6, which is 6 over 1, and adding on to 7 here. These 6's will cross cancel, so we'll be left with 7 plus 7, and that's equal to 14. Same thing over here, we'll have 7/6 times 6 over 1 plus 7. These 6's will cross cancel, we'll be left with 7 plus 7, and that's also equal to 14. Since 14 is equal to 14, this checks out. That brings us to example 3, where we'll try a few geometry application problems involving area and perimeter. Let's start by finding the area of this entire rectangle. To find the area of the whole rectangle, area is going to equal length times width. Our length is going to be this entire side right over here, from the left all the way to the right, and to get the entire length, that's going to be 18 plus 6. To show that, we can change L to 18 plus 6. For the width, we're going to put that right over here to the right side, and that's going to be 12. We can substitute 12 for W. Following the order of operations, we can add 18 plus 6 in the parentheses first, and that's going to be 24, so we'll have 24 times 12. And that'll give us an area of 288 square units. This would be the area of the rectangle. Now let's try finding the area of the two smaller rectangles and adding them up to see if it equals the area of the large rectangle. Here's our first rectangle over here on the left. And here's our other smaller rectangle on the right. To find the area of the rectangles, we're going to have to do area is equal to length times width. And we already know the length is equal to 18 plus 6, and we know the width is equal to 12. For the rectangle on the left, it's a 12 by 18 rectangle, so the area of that one is going to be 18 times 12. And for the area of the rectangle on the right, it's a 12 by 6 rectangle, so we can write plus the area, which is going to be 6 by 12. 18 by 12 is the length and width of the blue rectangle on the left, and 6 by 12 are the dimensions of the rectangle on the right. The area of the blue rectangle is going to be 216 units squared, and the area of the other rectangle is going to be 72 units squared. Finding the sum of these, we're going to get 288 units squared. And this should make sense because cutting the rectangle into two smaller ones should still have the same area. Now let's find the perimeter of this rectangle using the distributive property. To find the perimeter of any rectangle, P will equal twice the length plus twice the width. Since we know the length is 18 plus 6, we can write 2 times the quantity of 18 plus 6, since we know that's the bottom and the top of the rectangle, plus 2 times W, so it's going to be 2 times 12. Now if we need to use the distributive property, we'll start by multiplying this 2 times 18, and that's going to equal 36. Then we have 2 of these 6's, or 2 times 6, and that's going to equal 12. Hopefully it makes sense why we have two 18s, because we have an 18 down here on the bottom, so we have an 18 up here on top. We have a 6 down here on the bottom, so we have a 6 up here on top as well. 2 of the 18s make 36, and 2 of the 6's make 12. And then multiplying this 2 times 12, we get 24. The two 12s, or 24, comes from this 12 on the right, and this 12 on the left. Adding together this 36, 12, and 24, that's going to be a total of 72 units. Using the distributive property, this is the perimeter of the rectangle. And that wraps up this video on some more applications and understanding of algebraic and numerical expressions. Keep up the good work, and I'll see you in the next one.